Hello and welcome to the YouTube channel D Creations Resources. We are discussing different aspects from science, especially physics. And today let us talk about the concept of band gap, which is an important concept that comes under solid state physics. And a band gap is basically the energy difference between the top of the valence band and the bottom of the conduction band in a solid material. And this is relevant for materials such as insulators and semiconductors. Now, it basically represents an energy range where no electron states can exist. But it is very important because it determines the electrical conductivity of a material. As you know, conductivity is a very significant property when it comes to applications of materials. Now, it is presumed that you know what is a valence band and conduction band. So, just to remind you, a valence band is the band that contains electrons that are tightly bound to the atoms in the crystal lattice. And they are mainly involved in chemical bonding, while the conduction band is a band that contains electrons that are free to move within the crystal lattice, and they enable the material to conduct electricity. So, essentially, band gap energy is the amount of energy which is required for an electron to move from the valence band to the conduction band, becoming a mobile charge carrier. Now, conductors or metals have non-existent band gap. So, their valence and conduction bands overlap. And of course, you know that these are good conductors of electricity. Semiconductors have a moderate band gap, and it is very important when it comes to the use of semiconductors for electronic devices, because here the best part is you are able to alter their conductivity by adding impurities or applying external conditions. So basically you are able to modify or you are able to control the conductivity. And when it comes to materials such as insulators, the band gaps are very large. So as we know, they do not readily conduct electricity. Now, to give you some idea about the magnitudes, let's talk about two prime semiconductors. One is silicon, which has a band gap of around 1.12 eV, approximated to 1.1 electron volt. So, in other words, that is the energy which is required to excite an electron from the valence band to the conduction band. Germanium has even less magnitude of band gaps. It has a band gap of the order of 0.7 eV, to be more precise 0.67 electron volt. There are also wide gap semiconductors like gallium nitride or zinc oxide. Zinc oxide has a band gap of the order of 3.3 electron volt. So as you can compare with silicon and germanium, it's way larger as compared to that. Now there are two types of band gaps, namely direct band gap and indirect band gap. So they essentially refer to the nature of electron transitions between the valence and conduction bands. Now, direct band gap refers to the situation where the minimum energy of the conduction band and the maximum energy of the valence band occur at the same k vector in momentum space. So if you say if you plot energy E versus the k vector k, then in that EK diagram you will see that both the minimum energy of the conduction band and maximum energy of the valence band, they are occurring at the same k value. So here electrons and holes can directly recombine and emit a photon with energy equal to the band gap. And these are the ones which are suitable for light emitting applications like say LEDs or in lasers, and there are several direct band gap semiconducting materials like zinc oxide or gallium arsenide, cadmium sulfide, etc. As against that, indirect band gap refers to the situation where the minimum energy of the conduction band and the maximum energy of the valence band occur at different k vectors in momentum space. Now, this recombination of electron and hole is going to require a third particle to transfer momentum. So it will require a phonon, for example. So it's less efficient, so as to say. But although it has not, although it is less suitable for optical devices, it is useful for solar cells and in some electronic applications. And the elemental semiconductors like silicon, germanium are indirect bandgap materials. So we already saw the value of bandgap in their case. And this difference between direct and indirect bandgap semiconductors is very easily explained through an EK diagram. So if you just draw an EK diagram, you will be able to see the difference between direct and indirect bandgap semiconductor. Thank you.